my dear students. Today's lesson is an important lesson in mechanics. It's about work and energy. How are work and energy used in mechanics? The terms work and energy are used in everyday life, but what do they mean? In everyday life, a student who has been studying hard for 2 hours would say that they have been doing work, as would a gardener who has been working in a garden or an athlete who has been training. Each of these people has spent time doing an activity and has used energy. In the process, the energy comes from food that people have eaten. The gardener and the athlete have used energy to create movement, and the student have used energy to create brain power. Energy comes in many forms and can be changed from one form to another, and this issue we will discuss it. In this chapter, we will show that when a force moves a body, it does work and causes a change in the kinetic energy of the body. We need to speak about the weightlifter. The weightlifter does work in lifting a weight because a force acts like the tension in the arm of the weightlifter to cause motion. The weight is raised vertically. However, no mechanical work is done when the weightlifter holds the weight stationary above their head because there is no motion, so no work done. But it needs a lot of effort to just stopping the weight from falling. We'll start considering the work done by force acting in the direction of motion. Work done in the direction of motion. For example, pushing a horizontal force, pushing a box by a horizontal force across the horizontal floor. If the force is doubled, then the work is doubled. But if the force is constant and the distance is doubled, also the work is doubled. Because simply, as we can see on the board, work equals force multiplied by distance. The work is measured in joule, and the force is measured in newtons, and the distance is measured in meters. So, what is the definition of 1 joule? 1 joule is the amount of work done by a force of 1 newton in moving an object a distance of 1 meter. As we can see the boat in the sea, and this boat is moving just in contact with the side of a channel. And there is a pulling force which is not parallel to the side of the channel. This is not the force causing the work. The force that causes the work is this one I'll draw now for you. This is the component of it, which is in the direction of motion. So we'll learn that the force causing motion and causing work is the one in the direction of motion. As we can see a tiny little red arrow down, which is the contact force. It's perpendicular, as usual, we know it from previous chapters. The perpendicular force to the surface does not cause work. Why? Because it's perpendicular to the motion. The one which causes motion is this highlighted one. It is the component of the inclined force. Let's take some examples. Here's a boy uses a constant force of 250 newtons to push a box 4 meters across a floor. Find the work done by the force. W equals Fd. W equals Fd. Work equals Fd. Work equals Fd. So now let's calculate it. 250 Newton, this is the force. 4 meters, This is the distance, and we need to find the work. So W equals FD. We'll just multiply 250, multiply by 4, and the answer will be 1000 joules. Another example. A girl holds a mass of 20 kilograms above the head. Find the work done by the girl. She's holding like the weightlifter. We just said this example before. The weightlifter just carrying a heavy load and just preventing it from falling down. How much is the work done? 0. Why? Because it's constant, it's just stationary, and he didn't move it. So does this girl. She holds the mass of 20 kilograms above her head. How much the work done? 0. Because the mass does not move. The third one. A ball of mass 0.05 kilograms falls a distance of 1.5 meters. Find the work done by the weight. 0.05 kilograms, it falls distance of 1.5 meters. You know, dears, weight of an object is usually referred as the work done by gravity. The weight of an object is usually referred as the work done by gravity. So now, if the mass is 0.05 kilograms, this is the mass, but this is not the weight. Okay? So you have to find the weight, which is the force, which is measured in newtons. W equals mg. You just multiply the mass by the gravitational acceleration. In Cambridge, it is 10 meters per second squared. In Edexcel, it is 9.8. So this mass is 0.05 kilograms. You multiply it by 10. So the answer is 0.5 Newton. It falls at a distance 1.5 meter. You have to understand something, because this particle is falling vertically, and the distance is the weight is in the direction of motion, so it does work. So now work done equals W equals FD. W equals FD. We'll just multiply F by the distance, which is 0.5 newtons, multiplied by the distance 1.5 meters. It will be 0.75 joules. Remember, we are dealing with SI units. SI units, we said before, it is the MKS system. M means meter, K means kilogram, and S means seconds. And this is to get force in Newton and to get work in joule. Now we'll take an example of moving a box. You will move the box from this point to that point. This is the start and this is the end. So this is the distance moved from the center of mass of the box, from the beginning of the trip till its end. But the problem is we are pulling it with an inclined force F. So F is not acting completely to get the work. You have to find the component of force in the direction of motion. So we have to resolve this force into two components. One of them parallel to the direction of motion, and the other one is perpendicular to the direction of motion. Where is the direction of motion? Here it is. The component which is parallel, it is F, parallel to the surface, parallel to the direction of motion. It is F cosine theta. And the perpendicular component is F sine theta, which does no work. The component that does the work is F cosine theta. That's why we have to adjust the formula. Yes, W equals Fd if the force is in the direction of motion, but if the force is inclined, so it is F cosine theta into D. So Fd cosine theta, Fd cosine theta, Fd cosine theta. What is the title? It is work. Work measured in joules. Work equals Fd cosine theta, Fd cosine theta. Say it a lot. Then let's have an example. A small truck is pulled 5 meters along a railway track by a force of 100 newtons at an angle of 60 degrees to the track. Find the work done by the force. Let's underline every information and write the symbol above it. 5 meters, it is the distance along a railway by a force 100 Newton, but it is not along, it's acting at an angle 60 degrees. So this is theta, and this is the force F. Find what? Find the work done. Let's recite the rule. W equals Fd cosine theta, Fd cosine theta. Force is how much? 100 newtons. Distance is in meter? Yes, no conversion. Multiply by 5. Multiply by cosine 60. Remember that cosine 60 is half. By coincidence, it is half. It means that you will not take the full force. You are taking half of it only. So after multiplication, you will get to 150 joules. We need to mention something, that there is a force that opposes the direction of motion. Then the work done by this force will be negative, and we will say that work done is against the force. There is something else I should mention, that work is a scalar quantity. Work is a scalar quantity. It has no direction. Now next, we'll have here an example. A ball of mass 0.05 kilograms is raised through a distance of 1.5 meters. Find the work done against gravity. The word against here, we are using it. Here is the mass. It's raised. Distance 1.5 meters. Find the work done against gravity. Simply we will find the weight. W equals mg. So you will multiply the weight by 10, which is the gravitational acceleration, and the answer will be 0.5 Newton. This is the weight. So work done by the weight, work done by the weight equals Fd. So it will be force, which is 0.5, in the distance which is negative 1.5. So the answer will be negative 0.75 joule. This is work done by the weight. But if you want to say the sentence, which is work done against the weight, it will be negative the work done by the weight. Okay, so it will be 0.75 joule. This is the difference between the two sentences. Work done by the weight, it is negative, and work done against the weight, it is positive, because it is work done against gravity. Okay, work done against gravity. Sometimes several forces are acting on a body, like the one in this example. Let's read it. Here we have a box of mass 5 kilograms. It's pushed up a slope, inclined at 30 degrees to the horizontal by a force 30 newtons, at an angle 10 degrees to the slope. The frictional force acting on the box is 2 newtons. Of course, motion up, then friction down. Say motion up, then friction down. The box moves a distance 3 meters up the slope. First of all, we have to understand that writing the direction of motion is essential. Okay? The first question, find the work done against friction. The work done against friction is this pink force, which is friction, which is 2 Newton. So part A, the answer is 2 multiplied by 3, it is 6 joules. This is work done against friction. Next question. Find the work done against gravity. Against gravity, of course, he's speaking about the weight, but the weight is not acting as full weight. It's only a component of it. So we have to find the perpendicular component and the parallel component. If this is 30, not 30, 30. So this component is W cosine 30, which is not doing work, but W sine 30 is doing work. Hello, my dear students. Today we'll resume what we started about energy. Energy can exist in many forms: heat energy, light energy, nuclear energy, chemical energy, like from food or fuel, stored energy, which we call it potential energy, such as the energy stored in compressed spring, and so on. Energy can be transferred from one form to another and can be used to create motion. Energy is a scalar quantity. It can be positive, it can be negative, but it is scalar, like no direction, like we said before in work. And both of them are measured in joules, by the way. In mechanics, we are only interested in mechanical energy. And we have two types of mechanical energy: kinetic and gravitational potential energy. Kinetic energy is the energy that a body possesses because of its motion. A body of mass m kilogram moving with a speed v meters per second has a kinetic energy given by half mv squared. You just multiply half by mass by the square of velocity. Kinetic energy could be measured in kinetic energy, it is the red one. It is half mv squared, so it is measured in kilograms. This is mass, velocity, which is meter per second, and then you square it. And when you distribute the power, so it will be kilograms meter per second squared into another meter. So is this the units of measuring, which is Newton meter? Yes, it's the same. So why don't we name it joule? Yeah, it's the same. So it's the same units of measuring work. Here's a worked example. Find the kinetic energy of a body of mass 3 kilograms moving at 5 meters per second. You will just multiply. We need to find kinetic energy, mass, velocity. So KE is half mv squared. Say half mv squared. Half mv squared. Just calculate it. It is half multiplied by mass multiplied by 5 squared. The answer will be 37.5 joules. Second example. A body of mass 50 grams, not kilograms, hits the ground with a speed 10 meters per second and rebounds with a speed 6 meters per second. Find the loss in kinetic energy that occurs in the bounce. The word loss, it means you should find the kinetic energy, which is final kinetic energy minus initial kinetic energy. Okay? 50 grams, this is the mass, should be converted. This is the speed. No, this is the initial speed, and this is the final speed. And we need the loss in kinetic energy, which is kinetic energy final minus initial. Does this make sense? Yes, it does. So, first of all, convert. Mass equals 50 grams divided by 1000. To change it in kilograms, it will be 0.05 kilograms. And now we have to find the change in kinetic energy equals the final kinetic energy, which is half mv squared, minus the initial, which is half mu squared, and we just calculate half multiplied by, we can take half m as a common factor, but we cannot take the squaring as a common factor. We have to subtract the square of the velocities. Okay, so half into 0.05, I can open brackets and find v squared minus u squared, which is 6 squared minus 10 squared. Of course, we expect that the answer is negative because simply it is loss. But when we say the word loss, we remove the minus. Okay? So if you want to calculate each kinetic energy individually, kinetic energy before, and you find it in joules, kinetic energy after, and then you subtract them, no problem. So the loss will be, so it is negative 1.6 joule. So to say the word loss, don't mention the sign. Loss in kinetic energy is 1.6 joule. By the way, I'm reminding you, if you need to find initial or kinetic energy before, you calculate it. This is before rebounding. It is half multiplied by mass multiplied by 10 squared. And kinetic energy after rebounding, it is half multiplied by mass multiplied by 6 squared. You find both of them and then subtract. Next. Now we'll speak about gravitational potential energy. This is another type of mechanical energy, which is the potential energy. It is this energy, it is the energy that body possesses because of what? Only its position. Its position where? Above a certain base. You can choose the base and measure all heights from this base in this question. Gravitational potential energy that could be released if the body falls under gravity. So it is stored and waiting to release. Stored because of its height above a certain base. If mass m kilograms has a height measured in meter, its potential energy will be mgh, measured in joules. Potential energy mgh, potential energy mgh, potential energy mgh. The amount of potential energy that a body possesses depends on its height. The height is measured from a base level. At this base, potential energy is 0. We can choose any level, as I said before, to measure from. Now, here is a question about find the increase in potential energy in raising a sack of mass 1 kilograms through a height of 3 meters. Increase in potential energy. The mass, this is m, this is the height, and you'll simply answer like increase in potential energy. Mass is 1 kilograms. What is G? It is gravitational potential energy. So G is the gravitational acceleration, which is 10. And the height above the ground is 3 meters. So it will be 30 joules equals mgh. When a body of mass m is raised through a height h, the work done against gravity is mgh joules. Work done against gravity. And the increase in gravitational potential energy is mgh. So potential energy increases when the work done against is done against gravity. So objects at a higher level have more potential energy than those are at a lower level. When the same body descends through a vertical distance, h meters, the work done by gravity is mgh, and the decrease in gravitational potential energy is mgh joules. So potential energy decreases because the height decreases, right? And potential energy is directly proportional to the height. When height decreases, potential energy decreases too. Okay? So potential energy decreases when work is done by gravity. What matters the vertical height difference between the top and the bottom, even if it is sliding on a slope? We are considering the vertical height. Again, what matters is the vertical height difference between the top and the bottom, even if the body is sliding down a slope. The last thing to mention is the modeling assumptions. It's always, we are assuming objects as particles, even if this is often not the case. For example, the wheels of the car, they are rotating. So the point at the top of the wheel is rotating like that. It is faster than the car itself. And the point at the lowest point of the wheel is moving more slowly. But we will consider this difference as negligible and consider the whole car as a particle. This is the modeling. Experimenting with a ball rolling down a slope will show that the speed at the bottom of the slope is not as high as expected. All these are modeling, and we will handle it very soon. Thank you. See you in the next video with work, energy, and power. Bye-bye.